is Xiaopen Li, and I'm a associate professor in the Department of Civil and Environmental Engineering, affiliated with Qatar. Also director of the NICER Center, and I'm with Dr. Yu Zhang, core organizing this webinar courses. And today we're very fortunate to have a very well-known and scholar and very young, and I know, and also and he's my personal friend for a while. You know, you can see a number of great things from the bio. I don't need to repeat them. I could just tell you that you know I knew him while we were both friends, and we talked over receptions and over you know posters at conferences, and I witnessed you know he's soaring and becoming a rising star now. Is very established, you know. Though he's at assistant to professor rank, but if you look at his productivity, and he's way above that. He's I think he's not second to associate or full professor level. So I think you know I'll just stop from here, and you know I'll just have um, him to talk about his work on shared electric modular automated mobility. I would like to associate him with another professor who made a presentation. Her name is Monica Menendez. If you could remember, she was also from NYU, a different campus, and her talk was also about modular vehicles. With this, stage is yours. Thank you, Dr. Cho.
Yeah, thank you, Dr. Lee. And thank you for the really kind and generous introduction. In fact, I did submit my tenure package last summer, so I'm waiting for it this semester. So fingers crossed. Yeah, it's a real delight to be here today to share some of the work that we've been doing and just talk in general about this research trend towards you know, shared electric modular automated mobility. Let me just kind of advance this along a little bit. Okay, yeah. So just a little bit more about me. So my research focus is on urban transport and logistics systems, generally like the supply side of transportation systems in terms of modeling, and recently focusing a lot more on mobility as a service operations and planning for those, as well as the market evaluation. As Dr. Lee mentioned, we have a number of associations, including currently we have this NSF project that Dr. Lee is leading on, which is entitled Enabling Elastic Capacity for Transportation Infrastructure through a Transmodal Modular Autonomous Vehicle System. So it's really studying the capabilities, the technological capabilities of these this kind of technology where vehicles can couple and decouple on the move, and you know what that implies for mobility services. And as you can see on the right-hand side, I also want to mention that I'm a part of this C2 Smart Center. It's a tier 1 university transportation center that the focus when we developed proposed this center was to focus on the development of disruptive technologies as well as the technology transfer of it. So being able to connect between different cities to see that how new technologies can work differently in different cities of different sizes and characteristics. And we do have a consortium that consists of University of Washington, Rutgers, University of Texas, El Paso, City College, and NYU is the lead. So as this talk is essentially about you know how this modular technology plays a role in these shared electric automated mobility systems. Let me start off by talking about what is that first part, right? What is SEAM, this shared electric automated mobility? And this term has a lot of similar names in the field. If you search only for SEAM, you might not see the full literature, right? You might also have to do a little bit of digging using terms like connected autonomous electric vehicles. So there's a broad range of these vehicles, as you can see on this slide, having been in development, some in pilot tests, some in operations. I'm not sure even if, I think maybe your campus might have something, right, related to these services operating.
Yeah, we had a pilot test.
Okay, that's great.
Dr. Payson Ling.
Yeah, I mean, in New York City, they're not, as far as I recall, they're not allowed on the public roads yet. But there are some private facilities like the Brooklyn Navy Yard, where services like Optimus Ride, shown at the bottom, has been operating. So it's interesting to see, there is so much interest in this type of mobility system. So what is the draw? What is the attraction of having this kind of market? So the common point, talking point that people make in support of this, the SEAM technology is that there's a lot of synergies, right? You're essentially combining three different trends in technology research and development, right? Looking at electrification of vehicles, looking at automation of vehicles, and also looking at the operation in terms of sharing the service. Whether it's sharing the cars or sharing the routes and mobility of these vehicles for different passengers, and it's seen as a virtuous cycle, right? So basically one component adds benefits to another, which adds back to the other, right? So like a couple of factors are mentioned here. From an industry website, impacts like lowering costs because driverless vehicles do not have driver labor costs. Electric vehicle component can reduce the cost of charging because the driverless cars can access the charging sites on their own, right, remotely, without having a driver to connect them to it. Or like having the driverless vehicles, reducing the amount of congestion that they might have by offering sharing services so that they're more efficient in operations. So there's a host of these factors that have been presented on why the SEAM technology is so important, to the point that even recently, I think 2 years back, the World Economic Forum, they published a white paper talking about how they can develop a governance framework for SEAM, and they developed this prototype for North America and Europe, looking at this concept, right? So it's definitely very much supported, and an idea that is very much in development. There's a lot of research interest in this combined area right now. So then the question is raised that with all these proponents in support of SEAM, they oftentimes when they support this, they tend to ignore this question, which is essentially, are synergies enough to really offset all the added challenges, right? So oftentimes the planners and the policymakers, they push for this SEAM technology and cite all the benefits, but they don't go into some of the challenges that in this type of environment would end up being compounded, right? So that's part of the motivation for the talk today, in the sense that we want to point out that SEAM is a great goalpost to try to target, but it's not all positives, right? They're bringing that to the forefront requires having good capabilities to address a lot of the challenges that also come with it. And what are these challenges? So one example, and this is presented. I like the presentation of this challenge in this recent paper from De Ganzo and Jan van Ooyen, where they ran a couple of experiments using a model to look at various ranges of mobility on demand fleets, right? So from the perspective of shared usage, shared fleets, we can see that there are certain ranges, certain conditions where these mobility on demand services work best, which implies that there are many other conditions where they don't work as well, right? So like, for example, here we can see that there at some ranges, there's these DAR versus dial ride systems or ride sharing and so forth might work well, but compared to other situations, taxi services operating directly might be more efficient, or in other areas, just conventional fixed route transit would operate better. And so it becomes a very tricky challenge to try to identify the right conditions in which the mobility on demand or types of on demand services like microtransit would work best in those settings. And when we talk about SEAM, oftentimes we're thinking about SEAM as a type of shared mobility shuttles fleet, right? So it's looking at these SEAM services as essentially like electric automated microtransit services, and so there might be conditions where it's just better to operate other types of services. So we have to keep that in mind, because it's not a one-size-fits all solution that works best in every condition. So it's risky if you implement this in a place where it's much costlier and it leads to failure, where there have been scenarios like this, not even with the automated condition, right, but just with driver-based fleets, where this has led to failed implementations. And when this happens, the failures they tend to resonate much more with the public because they see these failures, and because a lot of these systems tend to be public serving, public supported systems, it can be harder then to continue to try to convince the public to use them in the future. So caution should be taken when considering that. And yeah, the point that these performances are further made noisy, right? In terms of like the conditions, it really depends on the algorithms operating underneath them all as well. From the electric vehicle perspective, we have understood in the last few years that electric vehicle fleets they need to share use of electric charging stations. The challenge with this is that electric charging stations have been very limited in number in the past. Right now, with the current administration and the recent proposal to invest heavily on electric vehicles and electric vehicle charging infrastructure, this may change for the US in the next few years. And that's very exciting to see. But still, there's this concern, right? Because the technology of electric charging stations, they still require much longer charging times. Even when you consider, some of the more faster technologies like the DC fast charging charging stations, they can take half an hour or more to fully charge a light duty electric vehicle, and so that's problematic, right? Because these operations with electric vehicle fleets, they depend a lot on the time management of these vehicles throughout the working hours. And so when you have to take out an hour out of the time to not just to charge, but to search for charging facilities so that they can queue up and be able to charge fully. That makes them less competitive. And we had another recent study in 2019 between Jae-Young Jang, who's at Ford Mobility, and myself, looking at electric taxis in New York City. And we saw that this having the need to just change some of the taxis to electric can actually result in significant competitive challenges for those vehicles compared to non-electric taxis. On this slide, what you see is a case study that we conducted a few years back for Seoul in South Korea, where we had optimized locations of charging stations, which you can see from the circles on the map. So in that case study, we looked at locating those charging facilities and then evaluating the performance of 600 electric taxis. And we compared that to the case where the taxis were non-electric. So like, if it's non-electric, what would happen, right? Compared to if they're electric. So compared to the non-electric case, by making them electric with the DC fast charging stations, it resulted in a decreased number of served passengers by 25%, decreased the average vehicle load by 25%. The operating costs in terms of the vehicle hours operated in total, they increased by 77%. Using the number of charging stations that we allocated to these locations with the capacities that they had. If you made them infinite capacity, so in essence, if the only concern was charging time, the operating costs still increased by 54%. And so this shows that with the combined limitation of the long charging time as well as the limited access, they really add significant cost to operations for these types of fleets. And that's another compounded concern when you include that with shared use mobility, right? So that's another thing to keep in mind. The third point here is with automated vehicles. It sounds very rosy that automated vehicles have been pitched as being able to reduce most accidents because they tend to be human driven errors and they can also add in a lot more efficiency in terms of operations. They can cruise more efficiently. They can valet park or operate in a more efficient manner, and so forth. And that is true. But there are still many things that are that need to be advanced in this area. So automated vehicles, by definition, rely on artificial intelligence, right? And a lot of the reinforcement learning applications for AVs thus far, at least as from what I've seen, they're still focused more on object and environment detection. Reasonably so. That makes sense. That they need to make sure that these vehicles can operate in all conditions, right? But they haven't gotten to the part where they're really learning specifics to passenger preferences. Which really is something that is needed because transportation services are services that link to user response, right? So it's important that we develop services that reflect that. And so right now, if the focus on artificial intelligence development for AVs only focuses on the non-user response aspect, then it's still missing that gap. As one of a more recent study that we did, we conducted this experiment where we hypothesized a hotel shuttle service to an airport in New York City, and we sampled travel times using Google Maps queries for 3 identified routes. With the point that for airport trips, the importance is that travelers have a very strong preferred arrival time that they cannot be late for. right? And so this preferred arrival time in terms of the departure time choice is very important. So when we take a look at a reinforcement learning algorithm, let's say one that's based on a multi-arm bandit algorithm, to select different routes to take each time the hotel shuttle service departs, if they do not consider unique user preferences like on-time arrival, it can lead to worsened performance, and that's something that we found in our study, right? So this is a third area from the perspective of autonomous vehicles that I think really needs to be further strengthened. Right? So there are still many gaps to really realizing SEAM, but it's very promising, right? It's an area that we want to push forward more. So what can we do? One option, which is the point of this talk today, is perhaps we can add a fourth dimension to this, modularity, right? So I'm guessing many of you have already seen videos or photos of this technology in the past. And this is essentially this automated vehicle technology that allows vehicles to couple and decouple on the go. So when we think about SEAM and allowing for the fleets and the vehicles to be modular as well, what can that do to the system, right? So let's look at this holistically now, right? So modularity being added to SEAM. So let's call this CMAM, right? For lack of a better term. So CMAM, one of the advantages that has been studied recently is looking at how having that technology can reduce out of vehicle transfer delays, and this is very important in in public transit operations, because one of the major impedances to transit ridership is that travelers dislike transfers. And so one of the ways that we can reduce operating costs, is to add more transfers, but passengers have a very high aversion to transfer delays. But what if we can make use of modular vehicles so that passengers can then make their transfers within the vehicle? And so when they get on a vehicle, en route, that vehicle might merge with another vehicle, such that the passenger can move over to the other vehicle so that they can decouple and go to their respective new locations. Right? That can provide significant savings, as I'll show you in the next slide. Another advantage is that with these, by having these en route transfers, we can also modify our vehicle routing algorithms. So these algorithms traditionally consider only pickups and drop-offs of passengers. But what if we can do that with transfers, synchronized transfers, in fact, right? So we've also conducted several experiments to see how this can improve the performance of the vehicle routing algorithms. A third case is that with these modular vehicles, then when they operate in sync, right? It's possible that the merged vehicles would have more efficient operations. So the cost of operating per mile might be reduced, right? Which leads to more flexibility in managing the economies of scale and achieving more savings that way. And that's an area that can be explored further, I think. The fourth one, and I think this is a very important one. In fact, this is a crux of the latter part of this presentation, is the ability of the vehicles to serve as mobile batteries, right? Each vehicle, when they're coupling, they can essentially, if we allow V2X types of electric transfers within a smart grid type of setting. These vehicles can transfer electricity to vehicles that have more depleted charge, so that this can result in the vehicles not having to necessarily make a long trip to a charging station and wait to recharge at that charging station. Right, so this can be a significant savings to the whole SEAM technology paradigm, right? And let me elaborate a little bit more on those examples. This is a study that we had conducted 2 years back with one of my master's students, and this was working with the next future mobility early on. We conducted some simulation experiments for this corridor connecting Dubai to Sharjah, where they do have bus fleets operating there. But we evaluated different scenarios considering replacing that public transit fleet where we had data for the transit ridership to 3 different other scenarios of operations. Right? One would be door-to-door, like a taxi service, which might also allow for transfers, right? Using our the on-route technology with the modular autonomous vehicles. A second would be just focusing the MAVs at the first and last miles, so that they're just connecting passengers and dropping them off at the transit station, and then using the fixed route bus service to transport people along the main corridor to the other city. Or a hub and spoke design where the modular autonomous vehicles would pick up people at the local origins and destinations, or I guess picking them up at their origins, connecting together into a platoon, a convoy of sorts, and then the MAV itself acts as the transit trunk going to the final destination. Right, so looking at the 3 different ways of operating this technology, we saw that there can be savings, although the range is based on different assumptions of transfer perception costs within vehicles. So like it was a pessimistic view, like if the transfers still were viewed as some kind of delay, what would it lead to? And we saw that generally profits improved and number of trips could decrease, but even with the number of trips decreasing, with the ridership, they were able to generally profit more in that kind of system. And so we see that having the modularity can definitely help in reducing the delay for having to transfer, compared to these changes are compared to having no on-route transfers at all, which means that those passengers would have to wait at the platform for their connections. Okay, so that's one example. The example of the vehicle routing algorithm improvement, we've also done some studies with that, and we saw that this is an illustration where we constructed a grid network where we can show illustrations where there are vehicles picking up customers from one place to another, and with transfers, with synchronized transfers, they can improve the operations. And we've developed heuristics to solve this kind of vehicle routing problem with synchronized transfers to pretty large scales. Here in this example, you see all the red diamonds are generated transfer locations as a result of the heuristic algorithm. So at the start of the run of the algorithm, these transfer locations are not selected. So it delivers the passengers and also identifies transfer locations to make the transfers for the passengers. So that work is ongoing right now, and Jesse Fu, who's also working, basically this is work that we're contributing to the current NSF project, and Jesse is looking to advance this a little bit more with the economies of scale incorporation and more detailed platooning capabilities. Right. The third example that I want to talk about was the mobile charging capability. Right, so there have been studies in the past about explicitly having like a mobility services to route batteries to different electric vehicles as a potential for saving time, because and they use battery swapping, but I think there's also been studies where they've had mobile charging units that would plug into electric vehicles to charge them as well, and there are ways of optimizing that. But that's an interesting research problem, because you have the operation of the electric vehicles throughout the day, but at the same time you have a fleet of mobile charging units that you also have to route throughout the day to connect them to the electric vehicles that have low state of charge to recharge them and allow them to go. Right, so it's having like a double routing type of problem. There have been like one or two studies that have looked at vehicle-to-vehicle wireless power transfer, and this one from University of Michigan is an interesting one that looks at that. But as far as I know, there hasn't been a study that has looked at MAVs as being capable of doing the vehicle-to-vehicle power transfer to the point that we can remodel the routing and the service of these systems to consider electric charging. Right. So I wanted to spend the next couple of slides diving into a closer look, because we're talking about the savings that you can gain from MAVs being essentially mobile batteries, but how significant can these savings be? So I'm going to share some work on some tangent research that we've done that looks at just some state-of-the-art electric mobility operations, but these are not MAV based, right? So this is just looking at mobility on demand services that are electric and trying to optimize their operations, considering the need to charge. Okay, so under this type of alternative system, let me just check my time. Okay, yeah. So under this type of electric system, there's really two main sets of operational policies that need to be considered while they're operating in real time. One is being able to match and route vehicles to serve customers, right? And the other one is how to deal with the idle vehicles, how to essentially rebalance them. And rebalancing really is basic. It's essentially considering a trade-off between two sets of cost savings. One is looking at relocation costs of the vehicles, right? The actual rebalancing act itself, and the accessibility savings. Because when you rebalance, you can increase the access to users at the destination that you rebalance to. And those are the trade-offs that are being considered, where the context is that the value that you derive comes from uncertain demand. You don't know what the demand is. So there have been a range of studies looking at these types of problems, stochastic models. I think Dr. Lee has done some work in this area as well. Right. So in the case of EV systems, though, the relocation purpose is essentially expanded beyond accessibility at current charge levels, and you have to think about it as accessibility for higher charged vehicles that we're trying to consider for. And a good way to kind of look at this is, let's say we have a one-dimensional network, right, where the two triangles there represent locations. The peaks represent the locations of charging of the vehicles, actually, where they're covering, and then that range represents the three nodes that they cover in terms of like areas where people might be able to access their service. But when you think about charging systems, now we expand the grid, that network one-dimensionally to a two-dimensional case where the second axis represents the charge level. So it's going from low to medium to high, right? So a vehicle at different locations may still, you might see, for example, the blue one is actually starting out at a low charge, but it's at a charging station that allows it to go up to a higher charge where it will be able to serve demand for high charge or medium charge or low charge vehicles. Whereas the red one might be just situated at a medium charge location. I mean, they might just be, medium charged, and they might be situated at that location, so they could cover the demand for those areas, but not people demanding a highly charged vehicle. Right? So that's the expansion that needs to take place for electric vehicles. So we want to tackle that challenge, and so we want to focus on the rebalancing policies. And when we talk about rebalancing policies, let's think of it as it's a decision that is being made, let's say every discrete time period, right? Like maybe every 15 minutes, every hour, and so forth. Right? For some services, they might be longer range, like electric car share, for example. The car share itself might not happen as frequently as like a electric taxi service. So those might be further, like a longer time range. So period by period or epoch from epoch, the system would have to reoptimize the rebalancing of these vehicles to different locations. The outcome of that decision is state dependent, right? And hence it's a policy that we're designing. It's a policy that depends on outcome of the previous decision and the transition that occurred. At the same time, the result of the decision impacts subsequent effects, which implies that when we develop these rebalancing policies, we need to consider the look ahead, right? What is you want to capture the cumulative reward of the policy for a whole horizon of the operation. And so when we're quantifying the impacts of decisions, the challenge with these kind of problems, especially with large networked systems, is the curse of dimensionality. And this is covered very well in a lot of Warren Powell's work. Right? Essentially, to tackle this, we would tend to need approximation methods. And there are 4 classes of approximation methods as listed here. The way that we're approximating the future states where is through a cost function approximation, which means that we're taking the cost function of the current operation and augmenting it so that it, in a way, captures the future cost. And the way that we're augmenting it is to add in the queuing delay, queuing effect. Okay. So far we have this alternative node graph structure. I kind of illustrated it earlier, but this elaborates a little bit more on the conditions, what it really means. So the type of problem we're dealing with here is a p-median problem. It's a facility location problem in terms of like relocating servers. I know that there are also studies where they've looked at rebalancing as essentially like a queuing network. The difference between the two is that with queuing network, you're actually not considering, like when a server is at a node, that server is only serving customers and demand arriving at that node. So that's the difference. Facility location problems or relocation problems are coverage problems. And so when you're relocating a server to a specific node, they're covering what they can cover within that accessibility threshold that you might have defined. And so we're looking at a p-median relocation problem where it's operating in essentially a node charge graph structure, right? So I'm using a single dimension node graph, but in reality, in operation, we're actually doing a two-dimensional graph. So it's really a three-dimensional structure. And when we talk about coverage, the part B in the figure illustrates that well, right? So essentially, that black diamond there, not diamond, the triangle, essentially covers all the nodes at those two layers. But the covering node 1 might have a longer access cost than covering node 4, node 3, right? And a second consideration is that you have some locations that have charging stations, and these are reflected by the vertical arrows. These charging stations are capacitated not at a link level, but at a path level, basically the whole column, because this is a charge representation. But for example, in C and D, the graph in C is essentially showing two vehicles sharing use of charging stations at node 3, whereas in part D is one vehicle using charging station at node D, right? And so they're all simultaneously accessing the charging station, and so we need to keep that in mind when we're defining the capacity constraints at those facilities. And the way that we do this, I'm not showing like detailed equations. So just we have a relocation optimization problem. It's a mixed integer linear program. The conventional way might be to have the access costs as a queuing delay term in the objective function, but that leads to a nonlinear expression. So we convert that using objective to constraint conversion based on reliability measures to a queuing utilization constraint. And so the P median, as I mentioned, we have the different coverage constraints. Relocation is expanded from a transportation problem, flow conservation, to minimum cost flow problem, flow conservation, where the illustration at the bottom shows how the capacity constraints have to be monitored. Usually, if we're dealing with even like 10 charge levels, so representing each 10%, it's still manageable if we have to enumerate all the different paths to run the capacity constraint there. And the Q utilization constraint is represented by this expression, which is essentially requiring that the utilization ratio, the lambda over mu, falls within some reliability constraint that is constructed using a piecewise linear approximation. Okay, so that's where that works. And the nice thing is if we relax this constraint that I show here, it becomes a myopic policy because now the future access costs are completely ignored. And so we can do comparisons pretty easily between myopic versus non-myopic operations. I can show you some illustration. This is taking that same grid where the red arrows are the locations. Node 2 and node 6 have charging stations. And when the capacity is 3, this is the solution. When it decreases from 3 to 2 to 1, you can see the changes in the solutions. All right. We propose a greedy heuristic to solve this problem. It's derived from the greedy heuristic from Teitz and Bart, but it's expanded to ensure feasibility at each iteration with regards to queuing constraints, capacity constraints, minimum cost flow relocation balancing, and demand access savings. So I won't go into details of that. And with regards to evaluation of the policy, we would need to run it in a simulated environment. We have real demand data, at least with regards to car share, but we don't have the actual, we want to be able to run it to evaluate the new policy. So for evaluation, we develop a custom simulator. This project is in collaboration with Professor Jabari and his student Li at NYU Abu Dhabi. We ran this case study for the Brooklyn fleet of BMW's Reach Now, back when they were still operating there. In fact, they closed down shortly after they shared the data with us. So we were very fortunate to be able to get that data. And shortly after that, after they closed down, they switched to they merged a couple of companies together to become ShareNow, and after that the ShareNow left North America to just operate in Europe. So again, this was a very fortunate time for us to be able to get access to this data before they closed down. This case study included over 300 traffic analysis zones. As you can see, the data for the demand is quite skewed in terms of like the duration of the reservations. The average is 6.5 hours, but the median is 45 minutes. It's because some people take the car share service for short trips, and then others reserve it for long periods of time, like a car rental type of service. And so you end up with more of this kind of bimodal distribution. We simulated a 30-day period where increments of time were at 1 hour. We assumed a 262 vehicle fleet, 18 charging stations, as you see on the right-hand side, with 4 chargers assumed each as the capacity, and 5 different charge levels. From the results that you can see here, the objective value does improve 38% over a myopic policy. But the thing I want to bring attention to and note that performance is very sensitive to availability of charging stations. Like if we add a few charging stations, it improves quite significantly. But the main thing is recharging at designated locations still leads to significant cost increases for the mobility service. And this is the point that with the SEAM type of service, without modular batteries, vehicles acting as batteries, this is the kind of cost that we can encounter. And so the last few slides here, kind of summarizing what can CMAM do, right? What does it be? The open research challenges with CMAM, for it to be really operational, we need to have rebalancing algorithms that count for electric charge transferring, power transfer. We need to have routing decisions that consider full economies of scale savings. We need to have incorporation of learning into the policies to deal with uncertainties of this emerging technology, particularly because we don't really have this in operation anywhere, so we don't really know how users would react. So there needs to be more direct learning incorporated into the algorithms to support the policies. And we need to develop a deployment portfolio model for CMAM technology that really identifies the best deployment opportunities, because as we showed earlier, microtransit itself has different areas where they operate best. And a last research challenge that I list here is how do we consider CMAM under a multi-operator setting, right? So they do not operate in a vacuum. There's a market of different mobility operators, some in competition, some as collaborative operators, right, for connecting people in multimodal trips. So it's important to be able to look at CMAM within that context. But I think that's maybe still a little bit further down the road. Just a quick overview of like the integrating the learning. We have done some work with using contextual bandit to like design routes to address having this flexibility in a sequential approach where there's high uncertainty, so that when you determine where to place routes or where to expand your service region, you have to take into account the costs of the added information that you can benefit from. And we're currently working on a project with VIA to look at how to develop a deployment portfolio model to support their expansion to different cities. And I think that's something that will be even more important in the near future for different types of mobility services to really like identify what are good conditions to operate in. This is just an example of some work that we're doing now with VIA, where we've been developing simulation-based approaches to evaluate a sample of cities, and then using that to kind of upscale the data, in a way, upscaling to a higher resolution data, so that we can help that to use that to develop portfolio models. And last but not least, the work that we have on mobility as a service ecosystems, looking at them as platforms, and then that would allow us to consider CMAM policies like having fare bundles or subsidies or leasing vehicle capacities and so forth. Okay, so conclusion, SEAM has potential, but as I mentioned, we should take caution because there are compounded challenges. We want to be able to offset those challenges, and one way might be to incorporate modularity. And these are some of the examples that we mentioned. And looking at the electric charging consideration, even with state-of-the-art algorithms, there are added costs, and CMAM might be able to offset some of those costs. And in future challenges, we want to look at integrated learning for deployment, evaluation of potential service regions at a portfolio level, and evaluating interactions. Okay, so that concludes the talk. These are just some acknowledgements, my contact information, the students that have worked on various projects that were listed as publications and throughout the presentation are mentioned here. And if you want to learn more about my work, I also share a screenshot of my book, Informed Urban Transport Systems. All right, thank you very much.
Thank you, Dr. Chow.
It took a little longer than I expected.
Yeah, well, it's great, and I think this is a very nice presentation with the breadth, good motivation, and some great technical detail. We're open to questions to the audience. If you want to ask questions, you can just simply unmute yourself and ask your questions, or you can leave a message in the chat box. It looks like we've already have a number of questions in the chat box. Let me just go through the, is that right? Let's see. All right, so maybe the first question is from Moid. Do you want to, if you're online, you may ask it yourself. Or I can rephrase the question. Just curious on slide number 8. Which airport in New York, JFK, or LaGuardia, your study area considered? Because
that was JFK, yeah.
Okay, JFK. Because the constructions at the airport building could delay the on-time arrival or departure of airport shuttles. Thanks.
Yeah, absolutely. And LaGuardia has been doing a lot of construction, almost unending. So yeah, that's absolutely right. But in this case, we were trying to look at this experiment in a sense of like AV algorithms. They tend to kind of ignore the passenger preferences. So we want to see what happens if they do consider it versus if they don't consider it. So thank you for the question.
Thank you, Moid Islam. He's a researcher at Qatar. Next is Xiaowei Shi, a graduate student with us. For the electric charging, did you consider exogenous impact factors to the charging efficiency, like temperature and transfer efficiency?
Yeah, we didn't consider those, but that would be interesting to look into that. When I think that's very important to consider when actually implementing that within different service regions. So you need to be able to customize that, but we didn't look at it in our algorithm.
Okay. Any other questions? Yeah, you may unmute yourself and speak out.
Hi, Joseph. I have questions. So, I mean, I really enjoy presentation. I mean, you have showed us the multiple research that you have done in this area, which are very impressive. I'm just wondering, for the charging, when we consider the electrification trend in transportation, so how the super fast charging will change some of the research that you have presented? And also, some researchers were starting on the switching the battery instead of charging. And I think that technology was also explored in other countries as well. So I was just wondering, faster charging and also, switching batteries, how that will affect the research that you have done. And then will that lead to, some potential challenges or other research directions from your point of view?
Yeah, definitely looking at faster technologies. I think right now Volkswagen, they're working with like this company QuantumScape, and there's these companies that are developing more advanced and faster charging technologies. So it seems to be coming down the road. But as of right now, though, even the DC fast chargers are very limited in number. So like looking at New York, for example, the company Revel, they're an e-moped company. They made big news because they implemented the largest fast charging hub in North America recently, and that was 30 DC fast chargers in one location. So it's not still not very prevalent right now. I think Tesla is doing a great job with putting more of the charging station, like fast charging, but those are still limited to only their own vehicles, right? As far as I know. So it's still some ways away. I think it would definitely help to have the faster charging, which would reduce the queue delay impacts. Because then they'll recharge faster, the service rate would increase, and that's something that would be reflected in the algorithm in terms of the mu for the service rate. Actually, not the mu, sorry, the time that the time that they take to go up the charging links. Yeah, and then the battery swapping that you mentioned, that's a really good point too. So the example that I showed on one slide, that was a mobile battery swapping service. And battery swapping has been proposed as an alternative because it tends to be faster to do the battery swapping. But I think it's still harder to at least implement that in a wide scale for a wide variety of services. I think for like a specific fleet that operates on their own, that's manageable. But like looking at this as like a shared public shared infrastructure, it seems like at least these agencies are looking more at the implementing charging stations right now. Yeah. But yeah, I think battery swapping is a great alternative to consider. Does
Sure.
that answer your question? Yeah.
Yes, thank you.
That's great. And we have Kim Fu Chul, and his questions. What are the him or her? I'm sorry.
It's a him. Yeah, I know.
It's a him. Okay. What are the financial cost considerations used for the AI to decide on charging station use versus switching batteries versus stop picking up customers when low in power?
You mean what are the cost implications of having the different choices?
Right. I guess financial cost considerations. Maybe, Kim, if you're online, you can further elaborate on the question. Yes, exactly.
Yeah. So yeah, I don't know the details of like the financial costs implications. I think battery swapping would tend to be pretty expensive. The way that they have to manage, it's a matter of the inventory of having the batteries and also having to keep them charged up. So it's it's a lot more charging management involved, I think, with battery swapping than with just having conventional charging infrastructure. But in terms of like, I think it's a trade-off, right? So like if the operations cost savings are high enough that they can offset that added investment cost, then that I think that would make sense.
Sure. Dr. Cho, I'd like to ask a question about the model. So it's a very innovative idea to use P-medium problem to investigate the planning decisions. I mean, when we talk about P-medium, that means we have fixed the demand, which is fine for a planning problem. But just to, considering some uncertainties, if we look into some operations problems or just consider certain uncertainties of the demand and travel patterns, maybe one possible extension is incorporating stochasticity of a demand, either using MDP or some kind of stochastic programming, or I don't know, maybe that's not going to much impact your results, but it might be interesting to look into the how the demand, the uncertainties would impact the whole problem structure and also the problem outcomes, the insights, and because you've been working on demand a lot, and that is interesting. Or we may think of something to maybe perhaps collaborate or or discuss further about that.
Yeah, no, I agree. I mean, in fact, the model that we have is dealing with the stochastic nature of that, because the demand that we're using, I mean, we're looking at the demand at that level, but we're also using the queuing constraint as a way of capturing the service delay that would happen for people arriving later in the future. So it's representing that steady state based on, looking at different decisions would impact that steady state.
Right.
So
the model
is
still static, right? It's you could use expected values, but sort of like the variances and other dynamics might be.
Yeah. It's basically, it's a static policy in that you run the model and that would, but you can customize the mules in these service delay constraint,
right.
For the future. You can update that over time.
Yeah, so. Just for some reliability design, I mean, one way is to optimize the overall expected cost, which static state is perfect, and just considering like service reliability, or I don't know, maybe there could be some more interesting problems to build upon what you're doing. Anyway, just my just some of the thoughts, and also looks like based on the operation modes, we have so many different dimensions now we can play with, like electricity, autonomy, modularity. It looks like with different combinations you can come up with different models. So lots of good things to work on. Yeah, that's great.
Yeah, it's a good time to be a transportation researcher.
Yeah, perfect. Any other questions? If not, let's give Dr. Chu another round of virtual applause. And we really thank him for his nice presentation. I myself learned a lot, and hope you'll enjoy the presentation. And next week we will have Dr. Larry Had from University of Arizona to give us a talk, and he's a well-known scholar in the area of connected vehicles, and I hope you can join next week. So thank Dr. Cho again, and hope to see you next week.
All right. Thank you very much, everyone.
Thank you. Have a good weekend. Bye-bye.
Thank you, Joseph. Good to see you.
Thank you.
Bye.